Hi everyone and welcome to this new video. In this video I want to talk about assembly programming. I want to introduce the core concept behind assembly programming, and also I want to showcase two simple hello world programs that you can write today right now in assembly. The first one is for x86, so the 32-bit version of the architecture, and the program is going to be this one, and we're going to analyze it line by line and see what it does. This program prints an hello world string and then exits. And the second one is the same version but for x86-64, so that we will see what are the difference between the different architectures, since x86 is for 32-bit while the 64 version is for 64-bit applications. But first we will start with some assembly programming concept. So as always, I hope the video is interesting, I hope you get something out of it. If you want to support my project, you can subscribe to the channel, and there's also a Patreon for those of you who wish to support me. Thank you very much, I really appreciate all the support and it pushes me to create even more in-depth content. So once again, thank you for the support, and we can get started by introducing some of the core concepts that have to do with assembly programming. So of course, the basic idea is that when we program in assembly, we have a much fine-grained control over the hardware architecture, and specifically over the exposed ISA of our hardware architecture. Now, what are the things that are exposed in the ISA? Some of them we have direct control, we have complete control. For some other, we only have indirect control. So we cannot control everything of the machine, just the things that were exposed to us by the designer of the architecture. Now, the first and most important thing that we have control over are the instructions itself. So we can call instructions over the CPU, over the architecture. Now, instructions can do a lot of different things. These things are more often than not about processing data, writing data into memory, reading data from memory, and things of the sort. And these instructions are encoded in opcodes that are known as operation codes. Now, I've made a video showing how you can emulate the chip 8 system, and in that process, the task you need to do to emulate the chip 8 is you need to implement all the opcodes of the chip 8. And the chip 8 is a very instructional project because it doesn't have many opcodes. Now, a processor like Intel x86, x86-64 is extremely complex. These processors, these architectures offer a lot, and I mean a lot of different opcodes, of different instructions. So to know them all is going to be crazy, but the most important ones are pretty simple. Like for example, consider this instruction. This is a classical move instruction that is used to move data between different memory regions. And here we are moving a fixed value, 1, into a register, which is a special area of memory, and we will talk in a short while about registers. So that's the idea of opcodes. Opcodes encode all the instructions we can execute on our machine, on our CPU. One thing that is important to realize about opcodes is that in the way they are encoded, they encode the instruction to execute and also the operands to use in that particular instruction. Like for example, in this move racks of 1, the actual binary encoding of this is going to include the move instruction, the destination of the operation, and the source of the operation. So of course, reading and decoding opcodes is as easy or as hard are as simple or as complex is the underlying machine that we are working with. If the machine is very complex, if it has a lot of instruction with a lot of different operands and stuff like that, it can become very hard. But basically, that's the idea, and today we will see a bunch of opcodes. Then we can talk about registers. Now, registers are like set of memory area that are inside the CPU. So the CPU has a set of internal memory locations that can be used for fast data storage and manipulation. These memory locations are known as registers, and they are identified in an assembly program through these labels. For example, these are the labels for the registers in x86-64, in the 64-bit version. In the 32-bit, they have slightly different names, because instead of the R, you have the E. So RAX, EAX. So basically that's the idea. Now in terms of memory, of course, there are different hierarchies of memories. And one thing to realize about memory is that we have a hierarchy of memory. And this hierarchy can be roughly described. This is like a very rough approximation. We have the hard disk, we have the SSD, then we have the RAM, then we have the cache of the CPU, and then we have the registers. So as we get closer to the CPU, we are increasing the access speed, how fast we can access that memory, but we are also decreasing the size of the memory. For example, in a 64-bit processor, the registers can only store 64-bit of information. The cache a bit more, the RAM a bit more, much more, and the hard disk much more. So the idea is that the more information we can store, the further we are from the CPU, the slower the access is. And this is like a basic trade-off of memory, and in the future maybe I can expand more on that. So basically the idea is that the registers are very fast memory location. We can access them very fast, and so they are used to store intermediate value for our computation, to call functions and things of the sort, to pass arguments between functions. It's like very useful thing to know and master. Then, as I was saying, we find the memory. This is the typical RAM memory, the working memory. It is slower, much slower than registers, but it is faster than the disk itself. And for example, consider this instruction. In this instruction, we are reading a value from memory, and this value is obtained by computing this memory address, RIP, so RIP, plus this hexadecimal value. So this becomes a number, and we use this number to index into the memory. Now, the way that our assembly program views the memory is an abstraction. It sees actually virtual memory, not physical memory. And what is the difference between virtual memory and physical memory? Now we can start by discussing physical memory. This is the actual memory in the RAM, in the physical RAM. So here we have different activation depending on the current load of the system. It is very fragmented, and a different process use this memory. So there could be something for process 1, something from process 2 right after. So it's a mess. It's really chaotic and it changes constantly. Now, when you program something, however, you do not want to consider everything else that is going on in the system. You sort of want to be sandboxed. You want to only consider your local context, your local process, your single program. Otherwise, it becomes extremely hard to program if you have to consider all the other programs that interact with memory. So in order to allow the single programmer to focus on his program and not on everything else that is going on in the system, they came up with this beautiful idea of virtual memory. And basically it is an abstraction. In virtual memory, each program sees the entire RAM as if it were only for their program, like if the entire RAM was assigned to their program. So they see it as a set of linear memory addresses. Now, of course, this is not really what happens, and the process of going from virtual address to physical hardware address is done by the operating system and the CPU. But we don't care about that if you want to work in assembly. You just care that you can index memory through addresses, and you can use linear addressing. So that's a really powerful abstraction that is offered by the CPU and by the kernel of the operating system. Of course, if you have to implement that abstraction, you have to care about how it works. If you just want to program in assembly, you can assume, you can take it for granted, and it really simplifies the act of programming itself. Then continuing, we find flow control. So basically, these are all the constructs that are used to implement conditional statements, to implement loops, to implement all these conditions in which we can execute certain instructions and not others. Now, one of the most important things to realize here is that the CPU, to understand which instruction to execute, the CPU uses a specific register known as instruction pointer. Now, in x86 and 64, they are called EIP in the 32-bit version and RIP in the 64-bit version. So for example, this memory address is computed starting from RIP, so starting from the next instruction. And this value, the value of the instruction pointer, cannot be directly controlled by the programmer. It's not directly controlled by the programmer. Why? Of course, because of security reasons and also just to avoid the programmer making big mistakes. Now, this value can be changed indirectly. For example, when we do a jump, we are pretty much changing this value through a jump. So we cannot move a value into this register, but we can use a jump statement to jump into a particular address, and this also changes the value of this instruction pointer. Now there are other types of jumps which are conditional jumps, which change the instruction pointer depending on a condition. And this condition is controlled by specific CPU flags that we will talk in a bit. So like things like jump equal or jump not equal, they are still jump instructions that modify the control flow by interacting with the instruction pointer, but this time you put a conditional statement to it. You say, you only change the instruction pointer if this condition is satisfied, if this CPU flag is activated. But before talking about that, we can talk about stack operations. So the stack is a critical data structure that is used by processors to handle a bunch of different things, such as function calling and to handle the local variables for a function. So when we program, for example, in C, we have different functions, like we have function A, we have function B, and we can call from A, we can call B, and vice versa, right? So that's the idea. Now, to support this abstraction, which is one of the most fundamental abstraction in programming, the concept of a function, it's really key to have a structured code that is easy to read, easy to maintain, or that is maintainable in general. So to support this abstraction, the hardware, the CPU, the ISA offers a stack, this particular data structure, which is fundamental in computer science, and it offers various instructions to interact directly or indirectly with the stack. To interact directly with the stack, we find the push and pop instruction, which is used to put element into the stack and to remove an element from the stack. And then there are also other instructions which deal with the stack but indirectly, the call and direct instructions. So they still interact with the stack, it's just that we don't see directly in the code, but underlying they are interacting with the stack. So the stack is fundamental to get used to if you want to program in assembly. So as I was saying, we find these CPU flags, certain numbers of instructions. So when they execute, they trigger specific flags in specific CPU registers. Now this flag is sort of like they trigger a state, no? They flip a bit into the CPU, and these bits are then read and used by conditional jumps, for example, by the jump not equal, the jump equal instructions, and there are other instructions like this. Example of operations that trigger CPU flags are the compare instruction or the test instruction. For example, if the result of this operation is 0, they trigger a specific flag into the CPU, which can then be read and used by the jump not equal and jump equal instruction. So basically that's the idea. And finally, as a last thing, I want to talk about system calls. So in the previous video, I showcased how you can modify a Linux kernel to introduce a new system call. So system call are the ways in which our software program interacts with the hardware through the kernel of our operating system. The program basically is saying to the kernel, hey kernel, can you write to this hardware device for me? Because I cannot do it, I do not have the privileges, you do have the privileges, this is your responsibility, do this for me. And so basically we have to call the kernel, and the assembly language offers us different ways to do this. Now if we are working in a 32-bit system, to actually trigger the kernel, to trigger the interaction with the kernel, the context switch to kernel mode, we use the interrupt instruction. We use int with the specific value 0x80. This will trigger a software interrupt, which will be handled by the operating system, and the operating system, for example Linux specifically, is configured to handle that particular instruction and use that particular signal, that particular software interrupt as a way to trigger the system call mechanism. So the kernel knows, look, I've got this software interrupt, I know this is a system call. In modern 64-bit versions, instead, we have the more direct and clear syscall instruction at the level of the assembly, which also triggers the system call. So basically that's the idea. Now, system calls, of course, are a mechanism that is implemented by the operating system, and it uses hardware resources, hardware mechanism. So at this point we have, like, this is of course just an introduction to assembly programming. There is so much more to say. It's just to get started and write basic, simple x86 programs, we just need this concept. Now, having introduced the basic concept of assembly programming, we are now ready to write our programs. So we can do touch hello32.asm, and here I'm gonna say yes. I'm gonna activate ASM mode, so ASM mode, and I'm gonna disable this. Okay, perfect. So how can we write our first hello world program in assembly? Well, we need basically two things. Like when you program, you have to consider always two different aspects: the data and the instructions, like what you're representing and how you're processing it. So let's get over with the data. So we will define a section called .data. This is the data section. In this section, we will put the string that we want to print out. Now, in our case, it's going to be the hello world string. How do we define this? We define the variable message. We define the DB, which stands for like defined bytes, something like this. It is used to define a sequence of bytes that will be put into the final executable. Here we put the quotes. Here we put the hello world with the exclamation point. Then we put the comma, and then we put the 0xa. And 0xa is the ASCII encoding for the new line character. So this puts in the message a pointer to the string hello world with the 0xa. So that's key. Then the next thing we need to do is we need to define the length of this string. Why do we need the length? Because we're going to use a system call write. We're going to trigger this system call, and the system call writes in the arguments. It requires a pointer to the string and also the length, like how many bytes of that string do we want to print out to the screen. So how can we get this length? So the len is another label. It's computed not with db but with echo, because it is a constant value that can be computed during the assembly of the program, during the production of the final artifact. And then here we put the syntax. We put the dollar minus message. So what does this do is it takes the current address of this line in the final artifact and it subtracts the address of the message. So by subtracting this, basically, since this appears right after message, we are computing the length of this string, because this string is going to fill up the bytes here, right? Hello, blah, blah, blah. And so if we start at this particular address and then we end at this particular address, this thing is the length of hello world. So basically, that's the idea. So this is the section data. Now at this point, we can define the section.text. This section instead will contain the code that we want to execute. Now in this text, we have to define as global a particular label called start. Now the start label, we can define as follows. We do the name of the label and then this colon. And the start label is pretty much the entry point of our program. It is similar to the main in C. When the elf executable is run, it looks for this start label. So this is why we need it. And by putting it global, we are telling the linker that the linker can actually see this label and the code that it contains. Now, finally, in here, we can start writing our code. So here we wrote the data. Here we wrote some metadata saying that the start routine is actually a global symbol. It can be viewed by the linker. I believe it is for the linker. And now we can write our assembly program. So the first thing we do is we're gonna do a write of one message len. So this is what we would see in C. In the C programming language, we would write write one message len. Now in assembly, what do we do instead is we have to move registers. We have to move values into registers and we have to trigger the system call. Now remember, we are writing a 32-bit program, so we will use the software interrupt handle, the software interrupt method to trigger the system call. But basically here we have to set up the arguments for this call. Now the first argument is actually not the 1, but it is a 4 and it is written into EAX. Why is that? Because into EAX we need to put the syscall number for syswrite, syscall index. It's the index for the syswrite system call. So each system call has an index, and when the user space program wants to call that particular system call, the program has to use the specific index. Now, different kernel version could use different indexes. Also, depending on the hardware architecture, you could have different index for the same syscall. For example, in in the 32-bit, so x86, we have 4 for the syswrite. In x86 64, it's gonna be 1 for the syswrite, because we have different hardware. So depending on the version of the kernel, on the hardware, it could change. So this is like a key point to understand. So this is the first thing. Then we need to put into EBX the value of 1. Why the value of 1? This is gonna be the file descriptor for stdout. So we're gonna want to print, we're gonna want to write into the standard output of the process, which is gonna be the terminal. So this is the first real argument of the write. Then we put the second real argument, which is the message. So here a move. Actually here it's move like this. And then we put the SX, so edx len. So we put the pointer to the message and the length of the message. At this point we can trigger our system call. And we can trigger the system call with the mechanism of software interrupt int 0x80. And here we can write make kernel call. So trigger, like this is trigger syscall, pretty much. So this is something that we can already execute. It's actually going to crash, but it can be executed. And we can see it in action. So once we have written this code, how can we bring this to execution? Well, here we have our source code in NASM. We can use NASM to, you can say -f-l32, elf32 to say, look, we want a 32-bit application. And then we're gonna generate an object file. Here I'm gonna remove my webcam and you can see the entire command that I'm using, NASM f, the source code -o, and then the output. Now this is gonna be an elf relocatable, an object file. And this means that this cannot be executed directly, but if we try to read it with a text editor, we get a bunch of binary bytes. So this is no longer in ASCII, it's a binary blob basically, and it follows the ELF format for objects. Now the last step that we need to do is we need to link it. We need to link it with to produce the final ELF binary. And we can link it manually with LD, so we do LD-m ELF i386. We put the object and then we put the LO32. And here we obtain the final executable. At this point we have an executable. This is going to be an ELF 32-bit executable. It's going to be statically linked and we can execute it as follows. Notice it printed a string, but it also went into segmentation fault. Why did it go into segmentation fault? Because here we did do the write, but we didn't do anything afterwards. Now this is not like programming in C. When we program in C, the compiler will emit code with a final exit at the end. In this case, we have to do it manually. So remember always to write an exit 0 if everything goes well. So how do we call an exit 0? Once again, we put the index for the system call into the EAX register, sysexit. Then we put into ABX the value 0. We can just sort it out because the status of this thing is like exit status is 0, so like nothing went wrong. And finally, once again, we call the 0x80. So we can do it again. We can first create the object, then we can compile it, and now we execute it, and we no longer crash out because we are successfully terminated. And look at this, if I get the exit status, I get 0. Now, let's say that I want to return a different value. So here I would move into EBX, for example, the value, let's return the value 5. So I can create the object file, I can link it, I can execute it. And now the return code is going to be 5. So I can control the exit status. Now in this case, it was good to have 0. So that's the idea. And this is our first example with 32-bit. Now, one last thing before we move on to the 64-bit. Now, if you notice, this thing was compiled into a static executable. Like if I do a file like this, it's going to say statically linked, which means that this is not a dynamic executable because we have linked it manually with the LD like this. Now, how would we link it manually to create a dynamic executable? So we would do -m elf i386. We put the same things as before. LO32, and then here we put lc dynamic linker lib ld linux.so.2, and then we put the l usr lib32 l lib i386 linux gnu. So we put this. Why did this work? Well, the lc tells the linker link it with the standard C library. The dynamic linker tells the linker to use this particular dynamic linker, which is embedded into the ELF binary. So this path is embedded into the elf binary so that when the elf binary is loaded into memory to create a process, it's gonna retrieve that particular linker, and then here we put the directories in which to obtain the 32-bit versions of the libc library. So basically that's the idea. Because we have linked it dynamically now, we can, if we do a file on it, it's gonna say dynamically linked, and if you do an LDD, we're gonna say, look, this is the user lib32 libc.so. Blah blah blah. But it still works. It's just that now it is a dynamically linked library, so it uses dynamic libraries. So that is it for the 32-bit versions. So we can just remove everything. I think we can just leave the code, and I'm gonna have the code, of course, in the description for the Patreon supporters within the private GitHub Git server, the private Git server. So this is Hello32. Let's create Hello64, and let's see that in 64-bit versions, not much changes. So what do we have here? Let's put this. So let's put the section data. The section data is pretty much the same. Here we put message db with the bytes, hello world, and then we put 0xa. Then we put the len equal minus message. Then we put the section text, and here we put the global start symbol, and here we put the label. Now, once again, we have a write one message len, and we're gonna have an exit of 0. So we're gonna have the same system calls. Now, what does really change between 32-bit and 64-bit? Well, one thing that changes are the registers used. So for example, in the 32-bit, we wrote EAX. So we wrote move EAX, and it was like 4. Now, in this case, we're going to write move RAX, no longer 4, but we write 1. Why do we write 1? Because 1 is the index for sys bright. So between the different versions of the architecture, the kernel change the convention for the syscall indices. So that's the idea. We move it into RAX. Then the first real argument to the syscall is no longer in RBX, but it is in RDI. So in RDI we write 1, which is also for stdout.fd, is the file descriptor for the standard output. Then we move the message into RSI, and we move the length into RDX. Finally, here, we do not longer have to write int 0x80, like this, but we can use directly the syscall instruction. And with this, once again, we would have a working program that crashes and that produces a segmentation fault. So how do we compile this? Here we have the source code, we do nasm f, we do L64, we put the hello64, and then we put the output, the object file, so hello64.object. And so here we have an object file. This time is a 64-bit relocatable. So to link it, once again, we can link it statically, like this, hello64, with just a simple ld command. And here we have the hello64. And if you execute it, it's gonna print a string and it's gonna create a segmentation fault because the execution keeps going. But after this is called, here we do not put any instruction, so the CPU will read anything that comes after, try to execute that, and clearly this creates a segmentation fault. So to actually terminate without a seg fault, we need to write the exit. We can do that with a move rax60. Why? Because 60 is the index for the sysexit in x86-64 in Linux, and then we can XOR out the register, so status exit status equals 0. And finally, we can once again call the syscall. And so we have our code. It's pretty simple, and we can compile into object. We can assemble it into object. Technically, it's not compilation because we already have the assembly code. We can link it as a static binary, and we can execute it. Hello world. And this is a static binary. What if we want a dynamic library in a 64-bit version? Well, we can do once again the linker. We're gonna say hello64, hello64. So we're gonna say dash show hello64. And then here we're gonna put dynamic linker. We're gonna put lib64 ld linux 86 64.so.2. And then we're gonna put dash lc to link it with the standard C library. And now we have a dynamic linked library. So look at this. I'm gonna say dynamically linked. And finally, we can just execute this binary to obtain the hello world without problems with a dynamic library. We can do LDD to get the dynamic libraries. So that's pretty much the idea. Now in this video, I show how to program a simple hello world in assembly. I hope it was fun. I hope it was interesting and you got something out of it. If you want to support my teaching project, you can subscribe to the channel. There's also a Patreon for those of you interested in supporting me. And if you subscribe to the Patreon, you get access to all this code and all this material. It is under a private Git server. So thank you very much, and to the next video.